For the paper image is worth 16 into 16 words. We will look into vision transformer concept, and we have key points which we will go through in the slides. Here we will see introduction and how we can transform from CNN to vision transformers, which is innovative, and how this mechanism works. And we will look into its components like the patch embeddings, the CLS token, positional embeddings, transformer encoder, classification head, which is MLP as well. And then at the end, we will see and compare the results. So let's start. The big picture is here that early models showed promise. They showed attempts, but were complex or limited in some way. Vision Transformer proves that with enough data, we will look into it in more detail. So, with enough data, standard transformers scale really well for image recognition. Let's talk about more into this and see how this works. Okay, so we have this figure, and this shows the step-by-step explanation. The step-by-step, the process that how vision transformer work. So we can see here, um, if we go through, yeah. Um, First of all, we have an image here. You can see in the figure, right? And this input image is divided into small fixed size patches, like you can see here, just like a puzzle, like cutting a photo into puzzle pieces, right? And then, for example, if you have a 224 by 224 hybrid image with three channels, then this is splitting into 16 into 16. We will see into this in our next slide. So we are dividing image into patches, then we are flattening. I mean, each patch is flattened into a vector form, which is important. And this vector basically will pass through the linear projection layer. You can see, let me highlight with the red. This is the linear projection layer. So we will pass the flattened vector to the linear projection. This linear projection is a small neural layer, and this will turn into an embedding, a numerical representation that is important. And after this, you see above there is the part of the positional embedding. So the transformer don't know the order or location of the things by default, like the patch, image patch. So you have to embed position. So this is added to tell the model where each patch belongs in the original image. And basically, since patches lose the original information, you see when you divide the original image into patches. So this lost the information, the original information, location that where pixel correspond to what. And so when flattened, so this is added. This positional embedding is added. Also, nearby patches have more similar position embeddings. So this is something which we need to know. And there is a CLS token, which I'm going to highlight with the yellow. So you can see this is the um, position embedding with the CLS token. This is added to the sequence, and now you can say what is sequence in our case. The sequence now become the token, the positional embedding, and the patch. So this token is what? This CLS token is what? This is used to predict the final class later, like this image is bird or of wall or car, something like that. So when passed to the transformer encoder, then you know that here we have patches, the position embeddings, the class token. These are fed as a sequence. Like in case of NLP, we fed into transformer encoder. So this encoder has two layers: multi-head attention, where patches learn from each other's information. Again, multi-head attention, and the other one is the normalization approach. So in multi-head attention, patches learn from each other's information. So they can give you exact class, the final class label. And normalization basically process the learned features. So this happened in multiple times, like L times the number of layers represented by the L. And then we have the MLP head, which is the classification head. After encoding, the output corresponding to the class token is taken in MLP head. This goes to a small neural network, which we are calling here MLP, to predict the final class, like classifying the image as a cat or what. So Yeah. Okay. Let's talk about more. Um, yeah. Okay. For the patch embeddings, here is the figure. You see, there is a dog image. Um, yeah. There is the dog image you see, and let me change the color. Okay. And this is divided into patches. And the above figure shows for the NLP where you are, dividing the text into different tokens. So same image is divided into image patches. Now for the image, we are converting into patches and then embeddings. We see in the right figure here, we have the image of the size, height into width into C means channel, the color channel, which is 3. And this is split into square patches of size, this P into P, right? And you can calculate the number of patches with this formula, like where you have to divide height into width divided by P square. And each patch is this patch. Each patch is flattened into a vector, and this vector is mapped to the size of D, which is latent dimension with the help of linear projection. So this is basically patch embedding. Now D, you can say this is number of feature in each patch. D is the number of feature in each patch. Like for suppose, if you have D equals to 268 or 768, let's suppose. So each patch is 768 dimension vector. Okay, so class token, and for the position embeddings, a special learnable class token is added to the sequence, which we already discussed in previous slide. Its final state will represent the whole image for the classification. And for the position embeddings, when we add, so the model knows where each batch belongs to what image, right? And uh, okay, for the, let me see. Yeah. So for the transformer encoder, um, let me remove this so you can see clear. Okay, so for the transformer encoder, uh, we talk about that. Mm, yeah. Okay. Okay. So for the transformer encoder, we have input the um, sequence, right? We have input this sequence, right? The class token, the patch embedding, the position embeddings. So this encoder has two layers, which I already mentioned. The first was multi-head self-attention, and the other was layer normalization. Then this is also associated with the MLP head, which is the classification head. And this classification head basically um, uh, has the two parts, you can say. During the pre-training, this use the two layers, and during the fine-tuning, this use the single linear layer. So basically, these layers takes the final embedding input, okay? And this single layer projects the embedding, which is taken as an input to the vector of the size, which will be equals to number of classes. Also, MLP this classification head will provide you the probability, and the higher probability of the input or embedding, the higher probability will give you the label class. That we consider as a label class, right? And this is how this MLP works. So there are the things that CNN have built-in properties like locality, like neighborhood structure, translation invariance. But Vision Transformer doesn't have this because it only learns spatial relations from the data. So you have to give more data, right? This means VIT needs larger data sets to perform well. But we do have the hybrid model option, like instead of raw patches, Vision Transformer can take CNN feature maps as an input. This is the another hybrid option. And for the patch embeddings, which are then extracted from these feature maps. Okay. And a special case here comes when you have a patch of size, let's suppose 1 into 1, then you just flatten CNN output to the tokens. Anyways, in short, we can say that Vision Transformer splits an image. If you see this image again, yeah, image into patches, then embeds them, adds the positional information, class token and passes them to the transformer encoder. The class token output becomes the representation, image representation for the classification. So unlike CNNs, VIT, which is vision transformer, has little bit in knowledge of the images because it learns from the spatial relations from the data, right? And so it relies on the large scale of the data to learn structure, spatial structure. And yeah, um, yeah. So okay, now let's talk about the results. Okay, if you see here the table, we have the ImageNet, the different benchmarks of the data sets. But for here, I will talk about this. Okay, so ImageNet, if you see here, which is 14 million images across 21,000 categories. So basically, this is the data set. And for this, for the vision transformer, when we applied on the ImageNet, we achieve 88% accuracy. And on the Cipher 100, this is the 60,000 tiny images with the 100 classes. So when we applied vision transformer on this data set, then we got 94 accuracy, which is good. And for the VTAP, we can see here with the 19 tasks. Actually, this is a mixture of different data sets. So when we applied this on the VTAP with the 19 tasks, then Vision Transformer gets 77.63 accuracy. So these numbers are very competitive compared to our traditional CNN like ResNet. And if you see that when we trained, let me highlight, yeah, when we trained, let's suppose this one, Vision Transformer model trained on GFT gives the better accuracy than the ResNet, which is, a powerful CNN. So there is another example that it also performs the same or better than EfficientNet if you compare. And EfficientNet is another top CNN models. So conclusion is that if you train Vision Transformer on large data set, then this can beat the best CNN models as well. For this image and the figure, the left side here represents the learned embedding filters. So these different filters are like basic building blocks. The models, and this shows the models learns from the images. This is same as the filters in the CNN. For this image in the middle center, this shows the position embedding similarities, which is with the help of cosine similarity. This shows the model understands where each patch belongs to what part of the image. So it learns the image structure very well. At the end, on the right side, attention visualization is represented, where you can see the color dots, and this shows the that how different attention head look at different parts of the image. So this is not just learning the pixels, but the overall image structure. Okay. And yeah. So once you apply the vision transformer, the large data set, so yeah, of course, this can be the CNN model. Okay. If you see this figure, here we see that for the top left image, this one, the small vision transformer perform worse than the ResNet when trained on these small data sets. So when the data sets become large as the size grows, so vision transform outperform ResNet. You can see in the above top left image. And the right side of the image represents here that ResNet works better on small data set, but this hits the plateau. And VIT keeps improving with the larger pre-trained data set, which shows the scalability. And here on the bottom, left side, on the average across the task. So Vision Transformer outperformed ResNet at same computation cost. Um, and Here, hybrid is actually the mixture of CNN and the transformer, which gives improvements at the same scale. So you can compare this here. And on the right side of the figure, on ImageNet, vision transformers achieve higher accuracy. Again, if compared with the ResNet, with the same computation. Hybrid only helps for the smaller models. Yeah, and that's all about the vision transformer. And this is very strong mechanism if you train on the large data set again. Okay, for the key takeaways and the future work, what we can do best is the self-supervised learning. Yeah. So instead of requiring the huge labeled data set, vision transformers can learn from the unlabeled images by predicting missing parts, rotations, and the relationships between the patches. So this is better. This reduces the reliance on costly manual labeling. Other thing we can do is object detection. So um, going beyond the classifying an image as a whole, like a dog, vision transformer can be extended to locate and identify the multiple objects within an image. So let's suppose bounding your boxes around the dog and the ball. And the third approach, what we can do is segmentation. Vision transformer can be used for pixel level understanding. So dividing an image into regions like separating background, sky, person in the car. So this is crucial for imaging in medical, autonomous driving, and the robotics. Um, in short, future work expands vision transformer just classifying images to learning without labels and understanding where objects are and what each pixel represents. So that's all about our key highlights and the insights from the paper. And we already explained that how vision transformer work. Thank you so much for the for being this presentation.